but it's just kind of fun to do it. Like the algorithms was. Okay. We started briefly before the break with a little teaser of the idea of randomization. And if you recall, we were looking at this question, and we said you're given a bunch of items. You're told that half of them or more are zero, and you want to find one evidence of an item. So I'm saying there's a lot of good stuff here. Find me one good thing, right? That's one way to think about this. And any deterministic strategy for doing this, where you just sort of go through and look at the items, it's going to take a while to find a good item, which is frustrating because if there is so much good stuff in my bag, in my array, why is it taking me so long to find it? And one of the ways to think about randomization, there are others, but one of the ways to think about randomization is a way for you to quickly and reliably get at something that you're looking for, especially when you know there's a lot of it available. And in this case, the algorithm is very simple. Pick one at random, check if it's zero. If the item in fact is good, and if yes, you're done. If not, keep repeating. And then we briefly talked about how you analyze how long it takes to run this procedure, and we ended up very quickly, and I didn't really prove this, but I claim that this is basically takes 2 steps compared to say n over 2. So there's a very simple illustration of the power of randomness, that it can actually make certain tasks a lot cheaper for various reasons. And of course, in the process of doing so, you will lose something. But you lose a certain amount of a degree of certainty in your result, either in terms of how long it takes to find an answer or how correct your answer actually is. So nothing comes for free. But having said that, the amount of benefit you can get from randomness is so much that it's worth it to sacrifice a little bit in terms of certainty. And as we will see later on in the course, you can make that level of uncertainty as small as you want. So it's a tunable knob. It's not like a fixed knob. You can make it depending on your degree of uncertainty or degree of desire for certainty in your procedure. You can turn a knob and make it go better and better and better without sacrificing the benefits of randomness. So as a design strategy, it's very, very important. In fact, most of the world we live in today would not exist without randomized algorithms. They are baked into every single thing. In fact, it's kind of funny when people talk about, at the same time they talk about hashing as being a wonderful tool and ask why they should learn algorithms in college. Because the whole reason why hashing works is because of randomness. And so it's become so powerful and so useful that it's sort of buried deep in the DNA of modern big data computation in a way that people often forget to see. Right? And that's often the sign of success. You don't even notice it anymore. It's so successful. So we can't, you cannot teach a class in algorithms in today's world without spending a lot of time on randomness. And unfortunately, we can only spend a certain amount of time. You could teach an entire course on randomness if you could. But what I'll do, again, in the next few lectures, is sort of hopefully give you a flavor of how to think about randomness, what kind of tools you can bring to your power. A lot of them are very simple tools. And one of the best things about randomized algorithms is that the algorithms will end up being very simple. It's the analysis that gets hard. Right? So in the class, you will struggle. But once you're out of this class and you want to use randomization, then all you need is the algorithm. Yeah, hopefully the analysis is being done by someone. And so as a tool to design algorithms, you'll find them very, very powerful. So again, we'll struggle to analyze these algorithms in class. They will be difficult. That's okay. But hopefully you will see why they work. Get the intuition why they work. And then when you have to apply them yourself, you will have some good gut instincts for when they will work. Now, many of you have probably not done any probability in a long time, if at all. If at all, that's a bit of a problem. But hopefully you've done it for a long time ago. And And so what I'm going to do today is a very, very quick, very high-speed sort of refresher of some of the basic concepts you'll need to be familiar with. And I'll also give you notes to read so you can brush up on them yourself. But these are things you need to know. And they're sort of fundamental sort of things about probability. And I'm not going to go too far down, but it'll turn out that things like what's a random variable, what's expectation, these are things you think you know, but you actually probably don't know as well as you think you should. And knowing those things really well is going to be important to understand how we learn. Okay? So we're going to start with that now. And so we'll start with sort of the very basics of probability as in terms of what we need to sort of talk about randomized algorithms. So, you all probably have some intuitive understanding of probability. And what I want to do now is put that intuitive understanding on a more firm, formal ground. So that when we get to more complicated things you want to discuss, you have the right rigorous understanding of these things you can translate in your head from intuition to what you want to say. So in particular, we talk about the probability of some, like think of a die, right? A die roll or two dice rolls. You say, okay, what is the probability that it's, that the sum of the two dice is 7, or something like that, right? So these are questions you come across all the time. More formally, you should think of this as saying that you have some kind of space, right? You have some space of atomic events, if you wish, individual events. And for now, we'll pretend this is a discrete space, just to make things simple, so I can use summations everywhere. In general, these might be continuous spaces, you'll have integrals everywhere. But just say you have some space of events, right? And this is usually called, many things, but we'll just use sigma for this. This is the space of events, all possible events that can happen, okay? To talk about probabilities, you have to have a way of assigning numbers to these events, aka the probability that an event might occur. Like you have to have some kind of map. So associated with this space, you usually have some kind of function. It's often called a measure, but we'll call it a probability because things will sum to 1, and that'll keep things simple. So you have some kind of probability that maps events, right, to some number between 0 and 1. And these mappings have certain rules, right? That's very odd.
You've just been experimented on.
I feel like that video where people are playing basketball and the guy, the gorillas walks by, you're not supposed to. Okay. A random event. Okay. So there are rules for what makes something a probability, right? There are rules about things need to sort of. There's this notion of what is called subadditivity. So basically, in short, the probability of a union of a bunch of events, right, will be less than equal to the sum of the probabilities, right, in usual. The probability of any event happening should be equal to 1, right, or something happening should be equal to 1, right. And if you look at the atomic events in the space, individual things, they will add up. Right? So you can think of events as subsets of subsets of atoms, right? So technically, maybe I should have written this as 2. This is a set of events. Right? So you can have any combination of events. You cannot start talking about probability till you have a space of events and an association of those events with numbers, which you think of as the probability of that event occurring, right? You have to start with that somewhere. And the thing is, oftentimes these things we think of these things as obvious. Well, if you roll a die, probability of 1 is 1 over 6. Yes, that's fine. But you have made that statement that is the function mapping the event die roll equal to 1 to the event 1 over 6. If I have a biased coin, if I have a biased die, it may not be 1 over 6, maybe something else. So a lot of what I'm telling you now is to sort of, in some sense, show you how we actually make explicit choices to model a problem in a certain way. And that's where problems come from, they're not automatic. This will be important later on because you might know, I have a biased coin with probability P of being heads. It's not off. So you think more carefully about what it means to have a probability or something or the other. Okay. Once you have events, right? So these are basically, you have events and you have a probability. And if you go back to our original example here, we said that the event here is what is the probability you stop in k steps. That's an event. You're doing something, you're running this algorithm, it runs for some time, and you say, okay, did it stop in k events or not? You can ask what the probability of this event is. This is a well-defined notion, even though the event itself is kind of complicated. Okay. Once you have probabilities of events, the next thing you need to be familiar with is the notion of a random variable. If you had to define a random variable, could you define that? What is a random variable? Maybe let's start with an intuitive understanding. What's a random variable? Intuitive, not formal. Anyone? If I said let X be a random variable, what goes on your head? Yeah?
I tend to think of random variables as being represented by probability distribution functions.
Okay, so a random variable in your mind is something associated with the probability distribution function.
Right.
Can you be more specific?
Perhaps. The probability distribution function represents the probability of any event, whether it's, let's call it discrete, occurs over the entire event space, and the actual realization of a random variable is some sample of that distribution.
Still, I'm sure I understand what a random variable is. I heard events, I heard probabilities, all those things I understand. I didn't hear what a random variable is.
It's the realization of a probability distribution.
What does that mean, realization?
A sample.
So random variable is a sample from a probability distribution.
Right.
Okay, that's one idea. Fine. A random variable is a sample from a probability distribution. A probability distribution itself is basically this, a set of probabilities assigned to events. So if I sample something from here, that's a random variable. Okay. What else? Any other sort of intuitive understanding of what a random variable is?
Non-determined?
It's non-determined. What does that mean?
That's all I got.
But when you say non-determined, what are you saying? You're saying something.
It's not declared ahead of time.
It's not declared ahead of time. You don't know the answer. You don't know what it is.
Right.
It's unknown. Is that what you're saying? Or it's unspecified.
I'm not sure.
Okay.
Something sort of like that.
Okay. What else?
Possible values the variable can take associated with some.
Sorry? It can take different values?
Yeah, the possible values it can take.
Yeah.
So that we can complete the probability of success.
So what is probability of success?
So we will have some n motive like if we reach that, this will be the probability of success.
But what is success?
That we have to
Decide.
Yeah.
Okay. So it's something to do with something that gives you a probability of success. Okay. So let me tell you another way of thinking about a random variable. A random variable is merely it's a function from the event space, let's say right now, to the reals. That's all it is. There's nothing more magical than that. It's just a function. It associates events or collections of events with values. For example, I have an event, coin toss is heads, right? That's my element, and then I take that event and map it to a value 1. Or I have an event, coin toss is tails, and map it to a value -1. That's a random variable. A completely different random variable it's not the same random variable. I have chosen to take the same events but encode them in a different way. That's a different random variable. I could do other things like this. A random variable merely is a rule, is a function from the event space to reals. In this case, could be more complicated, but that's just it. Okay? That's all it is. And it's important to think of this in this level of generality because we'll be defining all kinds of crazy random variables as time goes on. And so so when you say, for example, things like, I roll okay, let's say, for example, here, I said probability of stopping in k steps is 1 or 2 to the k. The expected running time, okay, well, running time is not an event. Running time in this case is going to be a random variable. It's a function from the event space, depending on the events of, did I find an element whose value was 0 to an actual number, the actual time. So the reason we go quickly from events to random variables is because once we have random variables, we can now talk about things like the expectation of random variables. A random variable is a numerical quantity, right? It's a function from event space list. So in other words, we can say, x, we can say the probability that x is equal to 1 basically is, the probability of the event such that x of the event is equal to 1. Remember, x is a function, right? So random is a function of the event space to values. When I write probability of x equal to 1, I'm actually writing a shorthand when I'm really saying what is the probability of the events that lead to x of this being equal to 1. And this is a collection of events, maybe multiple events. Yes? So when I say things like this, you should be thinking in your head something like this all the time. Well, not all the time, but at least you should get used to the idea. That this is a shorthand for something else. And I emphasize this point because I find that there's a lot of confusion in your minds, generally, in students' minds, about probabilities of events and values of random variables and interchanging the two things carelessly. And you have to be a little bit careful about how you think about them. They're very similar, but they serve different purposes. Events are the basic objects, random variables are things you do the top of them. Okay? And again, once you have a random variable, you can now talk of the expected value of a random variable or the average value of a random variable. There's nothing more sort of informal way of saying this. And what is that? Well, the expected value of a random variable, right, is basically the average value, right? So if I took a value at random, well, let me back up a second before I talk about expectation. We briefly mentioned the idea of probability distribution. Now we can talk about probability distribution because we can say the probability distribution of a random variable, right, is the set of probabilities associated with all the different values x can take. Right? So I can think of a plot. I can think of x here, right? This is x, and this is the probability of x, probability of a particular value of x, some value x here, and I can draw some distribution like this. Right? If you think of a Gaussian distribution, right? I have a Gaussian random variable, which means that it takes on values that have a certain probability of occurring in a certain way. It's a special kind of random variable. If I have a Boolean random variable, it looks like something. If I have something else, and so on, so on, so on. So once I have events and a measure, a probability measure, I can define random variables. Once I define random variables, I can talk about the probability distribution of the random variable. Once I have the probability distribution of a random variable, I can talk about its expected or average value, which is a way of thinking if I picked one value at random using this distribution, what value would I get? Right? Well, and the answer is, well, the expected value of a random variable, and again we'll assume this is discrete, so this is a sum over all values you can take, right? The x times the probability that the random variable is equal to x. So this nomenclature I'll use a lot, where the capital will denote the variable and the small letter will denote the actual value of x. Right, so what this is saying is that I look at the average value. It takes on, when you sample it, it might be this value with this probability. It might be a different value with a different probability. You take the average. Right? So, let's say that, the simplest possible example of this, we could say, let's take a 6-sided die. Right? The random variable associated with the die is the actual value of what we see, right? So the random variable associated with the die roll is the face, the number of dots on the face that's shown. That's one event. So then what is the expected value of this random variable? So let's say it's a fair dice. So the probability that we see a 1 is equal to the probability that we see a 2 and so on, which is going to be 1 over 6. Right? So I've created a random variable. I've said this die is fair, which automatically tells me now what the probability distribution of this random variable is, which means I can now compute its expected value, which should be sum over all x equal to 1 to 6, x times 1 over 6, which calculate, which is going to be 3.1. Now, there's nothing stopping me from assigning a different value to what I see. The value I see could be, oh, I will assign the random variable to be the square of the number of dots I see on the die. Maybe I need that for something. Then the expected value of that random variable will be very different. It will be the sum of squares. And then you calculate with the program. So all I'm saying is that these are all simple applications, but they all involve specific choices we make. We made a choice to record as a random variable the number of dots on the surface. Makes it like the default choice, but it's not the default choice. It just happens to be one choice. We made a choice to decide that the probability of seeing that particular set of dots was all equal across all the sides of the die. That's another choice we made. And then once we do that, we can compute expectation. Right? Okay. Once we compute the expectation, another quantity we'll often want to compute is the variance. Right? So one way to think about this is that the expected value is the average, right? How often what's the average value? But as you all know, if you try to compute the average salary of people in the United States, it'll look really large because Bill Gates and Bezos and other people like that. Right? It's not a useful number. What you'd like to know is, well, what's the variance? Right? Does your distribution, for example, so let's draw two distributions. This is a distribution from 0 to n. It looks like this, right? And let's say its mean is somewhere here. This is a distribution from 0 to n that looks like this. And its mean is somewhere here. Two distributions have the same mean, but they look very different. If, for example, you are looking at what is the returned, how long does my algorithm take to run? If I ran an algorithm that looked like the first case, it's like, I don't know, it could run anywhere between 1 step and 100 steps. Take your pick. The second one is like, well, for the most part, it's kind of near 50, but it can, with some tiny probability, it might be. You actually would prefer the second algorithm to the first, because you have a bit more certainty about how it's going to behave. So looking just at the expected behavior is not enough, you need more. And so with distributions, we like to know more than just the average, we like to know how it spreads out. And so the next level of spread is called the variance. It's the second order sort of moment, if you know these things. And how do you define the variance? Well, it's the average value of the deviation from the mean. And since the deviation is sign-free, you just want to know some deviation from the mean, you take a square. So the variance, right? So the variance of a random variable, which is often written as sigma squared, we'll just call it the variance, is equal to the expected value of a new random variable. Okay? And what is a new random variable? Well, the new random variable is equal to the old random variable minus its expected value squared. Again, because we don't want to worry about sign. So notice that I said you have to take an expected value of some random variable, so that's my y. Y is defined in terms of x. If x is a random variable, y will be 1, 2. This will generate some number, this is a constant, and this will generate some number. Right? And this is the variance. And it's not hard with a bit of algebra to show that the variance of a random variable is equal to the expected value of the square of the random variable minus the square of the expected value. Kind of nice symmetric thing. And the variance will capture how far out it goes. The more spread out it is, the higher the variance will be. The more concentrated it is, the lower the variance will be. Right? And it could be anywhere. The expectation tells you where it is, and the variance tells you how much it spreads out around it. There are many other things we could be calculating. There are sort of more general moments. So for example, you could say that the kth moment, or well, the kth sort of centralized moment is something like e to the x minus expected value to the k. And these actually give you other useful piece of information. The third order moment is called the skew, the fourth is called the kurtosis, and if you do stats, you can sort of play games with all these things. They can be quite useful. But for now, we won't worry about it. The point is that as you get to higher and higher order moments, you learn more and more about the behavior distribution. There's a general theorem saying that if you have two distributions and you know all their moments, then they have to be identical. So in some sense, this captures a unique signature of the distribution. So these are some basics you need to understand about manipulating random variables. That's going to happen a lot when we study randomized algorithms. And in that sense, I want to go back to what we just sort of saw earlier and look at the analysis a bit more carefully in the language of this. Right? So let's go back to our analysis here. So we talked about this algorithm. We said pick at random, check if it's 0. If yes, we're done. Else repeat. Probability of stopping, blah, blah, blah. We do this very quick analysis. But let's do this more rigorously. So we have an algorithm here, and we would like to analyze its behavior. Our problem is that we don't know when it will stop. Because every time we run it, it might stop at a different time. In other words, the stopping time of the algorithm is a random variable. Okay? Okay, good. So let's go back down here. So now we know the stopping time of the algorithm is a random variable. So the stopping time, let's call it t, is a random variable. So if we would like to know anything about t, we'd like to know what the probability distribution of t is. That's the first thing we need to know. We can't do anything until we have some basic information about t. Well, we already had that. We said, well, what the algorithm does is it tosses a coin, it picks a random index, it looks at that index value is 0. If so, it stops. If not, it continues. So we know now, we can think, what is the probability that the stopping time is 1? Well, that's a random variable. The stopping time will be 1 if what event happens? Well, you're not able. What is the event that will happen? Yes? The event has to happen that the first time you pick something, you see a 0. What is the probability that that event happens? It's half. We said half of them are 0. So the probability that t is equal to 1 is the probability based on the algorithm that a of I is equal to 0, which is equal to half. Okay? Okay, good. That's fine for t equal to 1. What about for t equal to 2? What is the probability that t equal to 2? What is the set of events that will cause t to be equal to 2? Again, every random variable is mapping from an event space to a value. What does t equal to 2 correspond to? It corresponds to not getting it on the first try, and then getting it on the second try. Right? So it's a probability that 2 events happen. AI1 is not equal to 0, and AI2 is equal to 0. Right? Now, we're choosing these things at random, independently of each other. If we have 2 independent variables, the probabilities multiply. So this is a half, this is a half, and this is 1/4. Right? And you can see how this is going to go. So the probability that t is equal to k is equal to 1/2. Now we have the probability distribution for this random variable, which means we can do all kinds of fun things now. In particular, we can compute its expected value. What's expected value? It's exactly what we said before. The expected value of t is equal to the summation over all x times the probability that t is equal to, I should call it t is equal to t. Well, we know that this will be equal to, just the way we wrote this, as summation of k times 1/2 to the k. For all k equal to 1 to infinity. Okay? And there's a bit of algebra trickery here, and I'll point you to some notes that tell you where to do all these things. And this will give you the value. But again, my point in repeating this analysis is to show you now how to think through this in a more disciplined way. Sort of identify the random variable, identify the events associated with values of the random variable, use that to calculate the probability distribution of the random variable, and then compute its expected value. Yes?
What is this expected value tell us about the algorithm?
It's telling us that the average value of the running time of the algorithm is the value here. Which means that if I ran the algorithm 1,000 times, each time letting it run to completion, writing down the numbers I got each time, right, and adding them all up, and then praying to the frequentist gods because it's a very frequentist view of probability, not a Bayesian view, and then that number would be this. Or rather, if I did this a gazillion times, that's a technical term, gazillion, and that would converge to this value. So we're looking at the average behavior. On average, what does this algorithm do? So we often say, oh, well, on average, it seems to be okay. Often we're pretty loose about it, saying, well, what we mean by on average is on the data sets we try. This is a much more formal statement. It's saying that the algorithm, regardless of what your input looks like, will do this on average, where the average is taken over the choices of the algorithm, not over your input. Right? Okay. There are basically two different kinds of randomized algorithms. There's this kind, and then there's the other kind. So, this kind of randomized algorithm has an interesting property. It always gives you the correct answer. It finds for you an entry that has AI equal to 0. But we don't know how long it might take. This is what is called, so it's always correct, and the running time is a random variable. This is called, why I'm not quite sure, a Las Vegas algorithm. Okay, and the defining characteristic of a Las Vegas algorithm is it is always correct, but the time it takes or the resources it consumes to give you the correct answer are random. There are scenarios where this might be what you need. You have to get it to be correct. You're willing to wait longer or less. Yes?
I was just going to say that it underpins like the very profit nature of Las Vegas casinos.
Sorry?
I was going to say the reason that it's called this is probably because it underpins the nature of the like profitability of the casino games.
That's able to be correct, except for what I'm about to say next.
Okay.
Or maybe you can still spit it out. We'll see. The other kind of randomized algorithm is one where the running time is deterministic. So it's not a random variable. It will run in 10 steps, for sure. But the correctness is a random variable. And this, for reasons again unbeknownst to me, is called a Monte Carlo algorithm. Would you like to try and make your rational again now? Are you going to make something about European socialism versus American?
I think it's named after the casino.
Yeah, what is? I once wondered whether there was a Reno algorithm, but that's so depressing anyway. So these are basically the two kinds of randomized algorithms you will come across. More often than not, you'll come across Monte Carlo algorithms. And if you thought about MCMC, yes, MCMC is a special kind of a Monte Carlo. It's a very special kind of one with a very special purpose. What's MCMC? Oh, sorry, Markov chain Monte Carlo. Those who take a machine learning. Yeah. See, this is a problem. I assume everyone knows everything in machine learning. It's all in the air right now. That's actually not true. So that's good. I'm actually happy with that. What does this mean in the context of what we just did? So suppose we had this procedure, right, that was trying to find this entry that had AI equal to 0. What would a Monte Carlo version of this algorithm be? The Monte Carlo version would be toss the coin. If it returns, if AI is 0, say here it is. Otherwise, say I give up and stop. Or run it 10 times or whatever and just stop. Just stop after some steps. Say, look, I tried. Okay, I tried my best. What do you want from me? Stop. That's a Monte Carlo algorithm because it always stops at a certain amount of time, but now you don't know if it's correct or not. So for a Monte Carlo algorithm, the question you're not asking is what is the expected value of the running time. The question you're asking is what is the probability that it's correct. So what is the probability that the algorithm that stops after one step and says, like, I don't know, is correct? Its probability is half, right? In general, if you have a Las Vegas algorithm, for reasons we will explain in a bit, and you just stop it early, like you're running this Las Vegas algorithm, you know it's always correct, but its running time is a random variable. You're like, okay, I run it for 100 steps, it probably failed. You will get a Monte Carlo, and you actually write down what the probability of success is. A more interesting question is, if you have a Monte Carlo algorithm, can you convert to Las Vegas algorithm? This is not obvious that this can be done. How will you do it? So I have an algorithm that runs in a certain deterministic amount of time, but may or may not give you the correct answer. Sorry? Until? So run the algorithm again and again till you get the correct answer. So here's a little puzzle. Suppose suppose I'm rolling a dice. And I want to see if I get a 2. I roll the dice twice, or rather dice once. Okay? And if I get a 2, I say, yeah, I got a 2, otherwise I say I failed. That's a Monte Carlo algorithm. My goal was to get a 2 and I didn't. I get it with probability. Fair dice. Thank you. Not mistake. 1 by 6. So the probability of being correct is 1/6. Its running time is 1. If we use your procedure, we throw it. Okay, no. Throw it. No. Okay, throw it. No. How long would it take? What would be? We know it will stop when it's correct, so we know we get it. Its running time is now a random variable. In fact, it's the same kind of random variable we had analyzed earlier, except that now instead of this probability being 1/2 to the k, it's 5/6 to the k minus 1 times 1/6 to the 1/6. Why is that? Okay. So let's see now. What is the probability that this algorithm terminates in k steps exactly? The one where we just roll the dice, see if it's 2, if not, roll it again, roll it again. Well, the probability of it terminating in k steps exactly is the probability of failing for k minus 1 steps and then ending at the kth step. That's why I said exactly k steps. Right? Okay, so if I fail for k minus 1 steps, the probability of failing is 5/6. Right? So the probability of t equal to k is equal to 5/6 to the k minus 1 times 1/6. So the expected value is k times sum of k times 5/6 to the k minus 1 times 1/6 k going from 1 to 3. And you can work this out, the answer will be 6. Because this is a special case of a more general property that if I have an event that occurs with probability p, the expected number of times I must run that event for it to happen is 1/p. It's a very cool trick. If you solve this, you'll actually get this. It's a simple exercise here. Okay. So you can convert from Monte Carlo to Las Vegas, but there was one catch. You said run it, see if you got the correct answer, and if not, run it again. So you can only convert a Monte Carlo algorithm to a Las Vegas algorithm if there's a way for you to check if your answer was actually correct. That may not always be possible to check if your answer is correct, because you might just be doing something and hoping you get a good answer. You may not know if it's the right answer. So you can convert a Las Vegas to Monte Carlo by stopping it early under certain conditions. You can convert a Monte Carlo to Las Vegas by letting it run till you get the correct answer under certain conditions. Okay? And so depending on your needs, you might either need something that for sure ends at a certain amount of time, or for sure gives you the correct answer. Okay? So again, you should think of these as kind of larger scale black box transformations you can apply to convert one kind of randomized algorithm to another kind of randomized algorithm. And I want to tell you about another black box. There are other black boxes looking at. There's one more important black box which we'll call amplification. So we said that we had this dice we were rolling, right? And the probability of getting a 2 was 1/6. Right? We like our Monte Carlo procedure, the fact that it stops at a certain time. What we don't like is our success probability is 1/6. That's no good. How might you take a Monte Carlo procedure with a certain probability of success and make it have a much higher probability of success? You know, without having this problem of, well, I can run it forever. What might I do? And the trick here is a trick called amplification. And you've kind of already seen this trick already. So the idea of amplification is that if I have a procedure, so let's say I have a procedure, so I have some kind of algorithm, and the probability of success is P. Okay? Suppose I run the algorithm 2 times. And let's say I can tell if I succeed or not. So now my new algorithm, A prime, let's call it A2, says run A twice. So this is my new black box. What is the probability of success of A2? Right?
P plus P.
P plus P. Wait, why is it? Again, what is the, think of it this way, the event I'm asking is that after 2 tries it's successful. Let's say it depends. Well, one way to say this, yeah, it's almost right? One way to say this is that the probability of it succeeding is the probability of it not failing. Or 1 minus the probability of it failing. What is the probability of it failing after 2 tries? The probability of failing after 2 tries is the probability that it fails on the first try and the probability that it fails on the second try. Okay? Which is 1 minus P times 1 minus P for independent trials. So the probability of it succeeding is 1 minus P squared. Which if you apply this thing called the binomial approximation will lead you to 2P approximately. But this is a more correct way. Okay? Suppose I ran it 3 times, then this will become 1 minus P cubed, right? Suppose I want a probability of success that's really large, really close to 1. So suppose I want a probability of success equal to 1 minus delta. When you think of delta as a really small thing. So I want a probability of success of 99%. So delta is 0.01. A probability of success of 99.9%. So delta is 0.001. Okay? How many times do I need to run the algorithm? Well, we can solve for this, right? So we're saying that 1 minus delta should be equal to 1 minus P to the K. Right? That means we want delta to be equal to 1 minus P to the K. Yes? Delta is a small number, so let's just okay. So let's just take logs on both sides. So we have log delta is equal to K log 1 minus P, right? And so if we solve for K, we get K equal to log delta over log 1 minus P. I don't like the way this is. I want to rewrite this expression. One second. I don't like it because these are both negative numbers. It's kind of like that. Yeah, I mean, I can multiply both sides by -1. So this is basically, a better way of saying this is something like this is basically log 1 over delta divided by log 1 plus b. This is a little trick I'm going to use here that, well, actually let me not do that trick. Let me just write it explicitly. Log 1 over 1 minus b. Okay. So let me separate these into two parts, right? So let me actually this is a so P is the probability of success of the original algorithm, right? This is the algorithm. And so you can think of P as a constant. It's some kind of fixed constant. What this is saying is that, roughly speaking, if I want the algorithm to succeed with probability 1 minus delta, I need to run it something like log of 1 over delta steps. So if delta is a very small number, like 0.01, so delta is like 1 over 100, what this is saying is that I need to run it log of 100 times to get the desired probability of success. The important thing about this is that you can amplify the probability up by running it a number of times that's roughly log of the amount of amplification it needs. Which is why you can actually get a lot of benefit from amplification without spending too much extra time in terms of running time. So if the running time was some p, you're going to run it p times log of 1 over delta times. The overhead is not too much. But you can get a much better probability of success. So this trick of amplification is an important trick because it allows you to say, look, I know I said I have this Monte Carlo procedure that has a probability of success of, say, I don't know, 2/3, something very small. But without loss of generality, I can assume I can run it a little bit more often, a constant number of times more, and make the probability of success any large constant I want. Okay. So that's what. So it helps you design randomized algorithms because you can say, look, I'll just make sure it succeeds with probability more than half, and then I can go crazy. Okay. So this amplification trick is something, again, it's a meta trick we will often use when we design procedures to make sure the probability of success can be as large as you want to be. And it's also why randomized algorithms are popular. Because in order to make them more and more accurate, this is the knob I was referring to. You just run them a few more times. And we'll see a few more of these kind of abstract knobs we can design to make a very simply designed randomized algorithm run better. So this is akin to when I said we divide and conquer, you don't actually have to divide the half and half. As long as it's kind of a constant factor, it's good enough because the recurrence works. This is the same spirit here. As long as you get a reasonable probability of success, you can crank, and it'll work very fast. Without too much overhead. Okay? Any questions?
This is a basic question, but when you calculate the probability 1 minus b of 3 when you ran a, for example, when you ran a twice, right? You calculate the probability to be 1 minus b of whole square. Why it's not 1 minus b into b? Like, isn't this the same as the probability of first event failing and then the probability of second event getting succeeded?
So, again, think of the event space. I am assuming here that I will succeed if any of the trials succeed.
Okay.
It's an or. Which means I will fail if they all fail. If you define success as they all have to succeed, then what will happen?
Then all of them should have probability b.
Right. So in fact, as you run them more times, the probability of success drops. This is not a case you want to repeat. So for example, if you're taking the GRE, and I tell you that your overall GRE score is the minimum of all the exams you take, you really don't want to take it more than once. Whereas I tell you it's a max, then you want to take it more than once. So it's an analogy to this. There are many other meta algorithms you can think of. For example, in this case, right, I could say, I'm going to run it a bunch of times and take the maximum value. Now you can say, okay, in that amplification process, how do I analyze the resulting behavior? That's a whole different process itself. Or you can say, I'm going to run this algorithm. It is correct with a certain probability. It's wrong with a certain probability. And I don't know which is which. Now what do you do? I'm not going to tell you if it's going to be assigned. but there are different meta reasonings you can apply to how to take a simple procedure that outputs. So you can think of the study of randomization, randomized algorithms, as a study of what do you do when your procedure is outputting answers with some degree of success or failure. How do you reason about overall? So one thing we've done is reason about the probability correctness. We've done a little bit of how to reason about the average case behavior. Eventually, we will do much more sophisticated reasoning to say, well, what is the variance of the overall procedure? What is the tail? What is the probability that the running time will be more than 2 times the mean? Right? We'll be able to make very sophisticated statements along those lines. And in the process, we'll design a bunch of algorithms as well. But this is kind of today is kind of a more of a meta journey. So okay, these are some of the tools we will be using a lot, and then we'll actually talk about some real algorithms. Okay, I'll see you on Wednesday. Look for the next assignment. So, okay, in terms of grading. So, I have to, homework 2 is graded. I have to unmute it. Homework 3 is being graded right now. Homework 4, which will appear today, is going to be on flows. So that should be a relatively simple homework. It will be just about taking a problem and trying to think of it in the language of flows. Homework 5, which will come out after this, will be a randomization. Homework 6 will probably be an approximations. That will complete the whole cycle. I know some of you had emailed me over the break asking me about the date. I'm still waiting to hear back from the university administration about how we do the dates if we can't do it on the official date. So I'm working on it. And then we have officers. Yeah. Oh, quick question. Yes. Before we leave.
Who's in charge of putting up the lectures? Because they're not updating the lecture number.
The videos?
Yeah, yes. They are uploaded, but I don't try to do it.
Okay, cool. Thanks.
Yeah. I mean, because the thing is, if the lecture number is not there, you still need the date. And the problem is we need to have either the date or the number synced so people know which video corresponds to
Yeah, but they have the date.
But the date has to be the date of the lecture. If it's uploaded 3 days later, that doesn't really help. Right? But then you don't know which date it corresponds to. It has to be the date.
Yeah, it was uploaded